and check out the OSPF database with the point-to-multipoint network type. Note that there are no network LSAs, just router LSAs. Here is R1's router LSA. Notice the point-to-point link to R3 and to R2. For the database to be consistent, the named router must also report itself as on a point-to-point link to R1. Each entry has a metric of 64. You can change this metric by adding a cost keyword to the neighbor statement. Note that neither entry indicates a mask for the subnet. Note also that R1 is reporting that it has two point-to-point links with the same IP address, 123.1. The mask is shown in the stub network entry that follows. It shows the IP address 123.1 with a host mask. Let's see how these entries look in the routing table. The host routes reported in the router LSAs show up in the routing table as /32 with an explicit next hop to the advertising router. Here you see an explicit route to the 123.3 interface address with a next hop of 123.3. It is these host routes that allow R1 to treat the multipoint frame relay interface as if it was actually two point-to-points. Each router on the shared subnet is represented by an explicit route. To get a feel for how this can help us, let's take a look at the routing table on R2. Note the host route to 123.3 with a next hop of 123.1. This says that to get to the other spoke, we have to go through the hub. Well, this is always true on a frame relay hub-and-spoke topology. The point-to-multipoint network type makes this explicit. Both the NBMA and broadcast network types hide this fact by treating the 123 subnet as if it was an Ethernet, and we could go directly from spoke to spoke. Consider that with the point-to-multipoint network type, the next hop is never another spoke, so spokes do not need maps to each other. This means we could rely on inverse ARP for our maps, if required. As we will see in a later presentation, the point-to-multipoint network type can simplify IP multicasting over a hub and spoke, because joins are always sent directly to the hub router. By modeling the hub and spoke as a collection of point-to-point links, the point-to-multipoint OSPF network type accurately reflects the underlying hub and spoke reachability. This can solve a number of difficult networking challenges. It could also be useful when you have a full mesh of PVCs but need to account for the potential loss of a circuit. It is the next best thing to simply implementing OSPF directly on point-to-point subinterfaces. It can be instructive to mix network types and see which will work or not work and why. You will find that as long as you mix within type and adjust hello times to match, it will work. You can configure any OSPF network type on any frame relay interface type. The only thing that won't work is configuring the point-to-point network type on an interface that actually has multiple OSPF neighbors. To demonstrate a mismatch, we will change our spokes from point-to-multipoint to point-to-point. Since each spoke has only R1 as a neighbor, it should work. The default hello times are 30 seconds for point-to-multipoint and 10 seconds for point-to-point, so we will change the point-to-point side. First we'll change R2 from multipoint to point-to-point. And we'll clear the IP routes. Now let's do the same on R3. And now let's check our routes. . R3 does have full routes, but the host routes for 123.2 and 123.3 are gone. Can R3 reach R2? We have full routes and reachability, so the combination of point-to-multipoint on the hub and point-to-point on the spoke does work. We have lost our explicit spoke-to-spoke routes through the hub. R3 does not have a host route to 123.2. Instead, it uses the connected route to 123.0/24, and R1 routes it. Let's see what happens when we try to mix network types. We will change the network type on R1 back to NBMA and see if we can sort out the result. Now let's check our adjacencies. After a few minutes, we eventually see that R1 has two good adjacencies. We're about to see, however, that good adjacencies are not enough. Let's check our routing table. Notice that R1 has only the connected routes. We would find the same is true on R2 and R3. Let's check the OSPF database. We have 3 router LSAs and 1 network LSA. First, we'll check the network LSA to make sure all the routers are listed. The network LSA lists all routers adjacent with the DR, and all the routers are listed here. Let's check the router LSA from R2. Note that the first line says advertising router is not reachable. This means that the information in this LSA cannot be used. Let's see what links R2 is reporting. R2 reports 1 point-to-point link and 2 stub networks. Here is R1's LSA. Notice that R1 reports a transit network with R1 as the DR and its loopback as a stub network. The problem is that R1 and R2 represent the 123 subnet as different link types, so the topology map is inconsistent. This is what happens when you mix broadcast network types with point-to-point network types. The fact that each frame relay PVC is fundamentally a different broadcast domain means that OSPF spokes cannot become adjacent. Studying how OSPF network types can be used to work around frame relay's limitations is one way to gain a deeper understanding of both protocols.